The first one is to establish concentration of the magnetization around its mean. Okay, and maybe let's see. Yeah, I think I can fill the gap, so it's okay. So concentration of the magnetization around its mean. And the second thing I would like to do is to give you an explicit expression for the free energy in dimension 1. Well, just to give you an example of cases where, I mean, sometimes in statistical mechanics you're lucky and you can compute explicitly the quantity. In general, it's not the rule. In dimension 2 and more, okay, so in dimension 2 there are some things you can compute, but it's much harder. And in dimension 3 and more, basically, yeah, there is nothing you can, well, you cannot know, there is no close formula for the free energy. I mean, people have looked for it for 70 years and they don't have a clue, so maybe there is a... Okay, so, let me recall the setup. So we have a box in ZD. We have some eta, which is a boundary condition, okay, which is just a spin configuration in ZD. We have a positive beta and some h in R. And we define mu lambda beta h eta sigma to be equal to 1 over z lambda beta h eta exponential h lambda beta h eta sigma, okay, where this is just the sum over all configuration of these weights. Okay, and the Hamiltonian, you already know what it is, but let me write it once more. So h eta lambda beta h, it's equal to, well, the sum over edges in the box of sigma x, sigma y times beta plus h times the sum over vertices of the box of sigma x plus beta times the sum over xy in delta lambda sigma x eta y. Okay, where these are the boundary edges. Okay, so then from this we have defined a free energy which is just the limit when lambda goes to ZD, 1 over lambda log Z lambda beta h eta, and it doesn't depend on eta, and this thing means along any sequence that converges to ZD in the Van Hoff sense, or that invades ZD in the Van Hoff sense, like they say in the book. Okay, so we have seen that this is defined everywhere. This is well defined, that it is convex. So in particular, the derivative with respect to h, which we call m beta h, is defined everywhere except maybe on a countable set. Okay, so when I mean countable, this means countable or finite. Okay, and this set, okay, it's just a set of H such that the derivative on the right is larger than the derivative, okay, is larger than the derivative on the left. Okay, it's a place where the derivative makes jump. Okay, so now what we are going to do today is, well, we call that m lambda is just the empirical average of the magnetization over the box. And what we are going to show is that asymptotically, okay, when lambda tends to ZD, this thing concentrates around its mean. Okay, we know that its mean converges to m beta h. This is what we have seen last time. Okay, and now we are going to show that, in fact, this random variable is always very close to its mean. Okay, so what the theorem is, if H does not belong to the special set, and lambda n, okay, exhausts ZD in the Van Hoff sense, then we have the following. So for all positive delta, there exists n0 of delta such that for all eta in omega, such that for all eta in omega, then what do I have? For all n larger than n0, mu beta, mu lambda beta h, okay, mu lambda n beta h eta m lambda n larger, okay, minus m beta h. Larger than delta. It is smaller than exponential minus C0 delta lambda. Okay, so a lot of quantifiers here, but well, the statement is kind of clear. If you take a large box, then m lambda has to be close to m beta h. Okay, and the probability to deviate from it, it decays exponentially in the volume of the box. So for instance, in Z2, like if you take square boxes, these things like decays like exponential minus n squared, so very fast. Okay, so let me before trying to prove it, let me rewrite it in some other manner. So first of all, well, saying that this is smaller than this, or that this is smaller than this, it's kind of equivalent. Okay, you just change the value of N0 and C0, and things will go fine. Okay? If this is valid with a factor 2. So basically, we can just show this inequality just for the probability that this without absolute value is larger than delta, and that this is smaller than delta separately. Okay? If we show that both probability decay exponentially, we are fine. Okay. So what we are really be going to look at is another way to say this is that we want to prove that, okay, the lim sup when lambda goes to ZD, okay, of the maximum over eta in omega of 1 over lambda, sorry, maybe lim inf, yeah, no lim sup, sorry, log mu lambda Okay, so what we want to prove is really this. Sorry, so smaller than 0. And what this means is that this is valid for the lim sup that you take over any sequence that exhausts it in the Van Hoff sense. Okay, because basically, I mean, and then this lim sup, basically this lim sup is the thing that you can call, well, then if the lim sup is negative, you can take C0 to be minus the half of this lim sup, and this will work. Okay, and you will have to take N0 sufficiently large. I don't want to worry too much about this part. It doesn't complicate anything in the computation, but maybe I just don't want to write eta. So we'll just consider free boundary condition, but it works all the same for the other boundary conditions. Okay. The only reason why this works is because the convergence here, you know that it's uniform in eta. And this is something we have seen. I mean, I've not said it, but when we saw the proof, we proved that the convergence was uniform in eta. So I'm going to take to consider the case of free boundary condition, and I'm going to prove the two bounds separately. Okay, so now let me come back to a claim that I made last time, which was the following. I told you. So now I'm not writing eta anywhere, just for the sake of being more readable. And what we saw last time, okay, what I said last time was that if m lambda was, well, the total magnetization in the box, okay, so the same thing as a small m, but without the taking the average, okay, without the normalization, then what we have is that z lambda beta h plus u over z lambda beta h, it's equal to the average of exponential um over the measure corresponding to external magnetic field H. Okay, and it is quite elementary, but let's write this. So when you write z lambda beta h plus u, well, it's a sum over sigma omega lambda. Then you get exponential h lambda beta h plus u sigma. And then you can say, well, I want to make h lambda beta h appear here because I want to write it as an average over this measure. So I can just say, well, this is this minus this plus this. Okay? And now this thing is simply exponential u. Okay, this difference here. Okay, so I just erase the Hamiltonian, but I mean here all the terms are the same except the term of magnetization. So on one side you have h times the total magnetization. On the other side you have h plus u times the total magnetization. So the difference is just this. Okay, so you just have this. Then if you divide it by z lambda beta h, you get this. Okay, and then this is just the probability of this configuration under that measure. So what you get is just really the average. Okay, so nothing super special here. Okay, so we are going to use this. And we are going to use this as follows. So we want to have a bound on okay, and for the moment, I want to have a bound on the probability that this is larger than m beta h plus delta. But okay, let's say that I just want this to be larger than alpha. I just want to estimate this probability, and then I will say, I will just check for which alpha I can get some results. Okay, so if I look at this, then I can say, well, okay, having this, it's exactly the same as saying that exponential lambda times m lambda times u is larger than exponential alpha u. Okay? Well, this is true as soon as u is positive. Okay? Just using the fact that the exponential is a strictly increasing function. Okay. And now I'm going to use something a bit more subtle. So what I'm saying is that, well, the probability then that this quantity is larger than this, well, this is larger than the average of this quantity divided by this. Okay, so So let me write m lambda here. Okay. And exponential minus alpha u. Okay, so this is just because, you know, this average here, you can always say that it's larger than exponential alpha u times this probability. Okay, so this is what is called Markov inequality. But I mean, really what this amounts to is just a lower bound on this integral. Okay, now, well, I can replace this by the quantity I had. So this is z lambda beta h over z lambda beta, so h plus u over z lambda beta h, exponential minus alpha u. I'm sorry. Here I forgot. I'm multiplying by the size of the box on both sides, okay? Because here I want the total magnetization. Okay, so I have to multiply by the size of the box here. And I mean, anyway, I want to have things that decay like the size of the box on the exponential scale. So obviously, this is the right thing to do. So, I mean, here already you see that things are kind of going on the right direction because okay, if I do things well, maybe I will get something, well, exponential of something negative times the volume. Okay. Okay, so now I will just rewrite this, but I will take the log and divide by 1 over lambda. Okay, so what happens if I do so? What I get is that 1 over lambda times the log of mu beta h lambda m lambda larger than alpha. Well, this is smaller. Okay, so then the first thing I get is 1 over lambda log z h plus u. So this is exactly f lambda beta h plus u. The second thing I get in the denominator is, well, the same thing with a minus and h instead of h plus u. And then I get minus alpha u. So now if I take the lim sup, okay, so I just write like this for the lim sup. Mu beta h lambda m lambda larger than alpha. Well, this is smaller than f lambda h plus u minus f h plus u minus f beta h minus alpha u. Okay, and actually this is valid for every positive u. So I can say this is smaller than the infimum over u positive of this. Okay, so now I just want this thing to be negative. So what I can do is take u into factor, u is positive, and kind of look at the rest that I have. So if I look at this quantity, I can rewrite it as f beta h plus u minus f beta h over u minus alpha. Okay, and now I know that this thing, when f is convex, so this thing is increasing in u. Okay, so my best chance for it to be negative is to take u as small as possible. So, and just hope that I'm smaller than alpha. So it turned out that the limit when u goes to 0, it's exactly the right derivative of f. So if f is differentiable, the limit when u goes to 0 is exactly m, beta h. Okay? So it is that if alpha is larger than m beta h, then take u0 such that f beta h plus u minus f of beta h okay, is okay. If alpha equal m beta h plus delta, I take u0 such that this is smaller than m beta h plus delta over 2, which is always possible. And I get that this is smaller than u0 times delta over 2. Yes, minus u0 times delta over 2. Okay, so this gives me a negative bound on the lim sup. So I'm happy. And you can see that, yeah, I mean, this works only if you take alpha. Well, if alpha is not larger than m beta h, then there is no hope to get anything here. Okay? Because this infimum will be 0, so you will just get the probability smaller than 1, which is not very interesting. Okay, so if this is the first time you see this kind of computation, the intuition is kind of intricate, but yeah, the idea is that the overall idea is that the average of the exponential of a random variable, it contains a lot of information concerning the probability of this random variable deviating a lot from its mean. Okay, and this is what we are using here. Okay, and I think the more you manipulate this kind of stuff, the easier it will be to understand. So any question before we go to the lower bound? So I will try to not to make mistakes, but the lower bound is basically you take the same computation and you kind of revert all the signs. So let's try to do it. So what we want to compute is, what we want to estimate is now, put it in purple, no, green. What we want to estimate is this. Okay, and so now what we are going to do is, well, okay, if you want to, okay, you may consider U positive, but now you want to consider so you want to revert the sense of the inequality, okay, in order to be able to apply this Markov inequality. So what we are going to consider now is not exponential u, but exponential minus u, or if you want exponential u, but for something negative. Okay? So now by Markov inequality, this is smaller than this, okay? The average of this quantity divided by this quantity. Okay, and I'm dividing, so the minus becomes plus. And now I get this and this. Okay, so I think so far I've not made any mistakes. Let's see if we can keep on like this. So now this should be what we get. Okay. We have a minus here, and we have a plus here. So this is all that changes. So we get that this is smaller. So you can always take the infimum. This is true, but you get a minus here and a plus here. Okay, so now we can do the same thing as before. What we have is really U times alpha minus F beta H minus F beta H minus U over U. Okay, so this is positive, so we want this thing to be negative in order to be able to conclude. And you know that when E converges to 0, this converges to M. Okay, for the same reason as before. I mean, this really converges to the derivative on the left this time. Okay, okay, I placed ourselves in the case where the derivative on the left and on the right exists. So basically, now if alpha is equal to M plus beta minus delta, then we take U0 such that okay. we want this to be larger than this, and we are done. Okay, you have m minus delta. You're subtracting something which is larger than m minus delta over 2, so you get the same conclusion here. Okay, so maybe a few remarks, or maybe an exercise, because it's good to do this computation once more. So I think I stated the result last time, but state a similar result for H. Okay. I mean, basically, state the best result you can for the magnetization when F is not differentiable using the same technique. Okay? I mean, you see that here we have used the fact that F is differentiable. I mean, just in the end, so you can probably do something even when F is not differentiable. Okay, so this is the first remark. Okay, basically you have to do the remark. The second remark is, okay, so if you see this kind of thing for the first time, well, it already seems extremely powerful. You know, this thing that just looking at the free energy, you can have this kind of bounds on the deviation of the magnetization. But it's in fact even better than that, in the sense that this lim sup here, it's actually a limit, and it's exactly equal to this infimum. So if you take the optimal u, you really get the true value of the exponential decay. Okay, so I mean, basically, getting a lower bound for this is a bit more complicated and advanced, but it's just something to know that, like, I mean, like, basically, I mean, it's not that when you're doing this, that when you're applying this inequality, you're not losing anything. But you're not losing anything in the exponential scale as soon as you take the optimal u. This is what this tells you. Okay, so yes, I think this is what I wanted to say on the problem of deviation for the magnetization. So for the rest of the class, we are going to do explicit computations in dimension 1 and diagonalize 2 by 2 matrices. So I will need your help for that, I think. So any question on this? Yes?
Do we have some similar result for Curie-Weiss model, let's say in the low temperature region?
Yes.
For the concentration, yeah.
Yes, yes. Yes, yes, yes. And the rate of concentration is n, just the size of the system. Yes, I mean, so the Curie-Weiss model, it's the Ising model, but instead of considering a lattice, you consider the complete graph. So just a graph with n vertices when you have all edges. And then you consider, instead of beta times the sum over xy, sigma x, sigma y, you just renormalize this by n, because, I mean, each vertice has n neighbors. So it's kind of better to normalize by I mean, basically, you want the two terms to be to act on the same scale, okay? So this thing could be n squared. This thing would only be n. Okay, so this, because this is. So if you divide it by n, these two things have the same. They are kind of competing, and this makes the model more interesting. Okay, so this is the model studied in chapter 2, and this is kind of a, well, this is what physicists call a toy model. So it's an easier version of the Ising model, for which you can basically compute everything. And by the way, I've not said anything about it, but there is the same kind of toy model for percolation. So you can also consider the complete graph and percolation with a parameter P, which is now some value over n, okay, just because same thing, if you want, I mean, you want each vertex to have, you want the average number of open, I mean, you want the average number of adjacent open edges to be finite, okay? And yeah, basically on this thing you can see a transition, and you can compute P, and you can say many things. You can even say what the system looks like at criticality. So yeah, these are interesting things. I would definitely talk about them if I had 4 months instead of 2. But maybe it's good also to have only two months. I don't know. More questions? So okay, this is what is called Curie-Weiss model. And this thing is what is called R de Shreni. Shreni, yes, I think that's random graph. Okay, and they are, well, okay, they are called either toy models for the models on the lattice, or also mean field model. And the idea is that everybody interacts with all the neighbors, so everybody kind of sees the average of all other neighbors. So this is the reason why it's called mean field. Okay? I mean, basically, each vertex here feels a magnetic field, which is basically the average of the mean of all the other spins. Okay. So now we can have a good transition. What's another model which is kind of a toy model in a sense that it's easy to solve? It's not a very good toy model because the result we get is not that interesting. I will come to that in a moment. But it's the Ising model in dimension 1. Okay, and what's a theorem? It's f beta h is equal to log exponential beta hyperbolic cosine of h plus square root of exponential 2 beta hyperbolic cosine of h square plus 2 hyperbolic sine of 2 beta. Okay, so this is explicit. But what you get out of this is that, well, f is So f is differentiable everywhere. Okay, in fact, it's analytic in both h and beta. Okay, in the sense that you can expand it in power series at any point. So B beta equal empty set for every beta positive. And what else? And you have no spontaneous magnetization at any beta. So remember, spontaneous magnetization, it's like the limit of the magnetization when you make h tend to 0. Okay, and what we would expect was that for beta large, this should be positive. And for beta small, this should be 0. And the idea is that this positivity of the spontaneous magnetization, it kind of indicates that the magnet keeps its magnetization when you turn off the external magnetic field. Okay, so, I mean, in dimension 1, the model is kind of a failure because we don't get a result that kind of fits the experiment. So for the story, the Ising model, it was not really introduced by Ising. It was introduced by, it was proposed to him as a PhD subject by his director, which was Lenz. I don't remember his first name. Well, Ising as a PhD student solved the model in dimension 1, said that, well, there was no phase transition for this model, and that probably it was also the case in higher dimension, so that they shouldn't study, that it was not a good model. Actually, after his PhD, he left academia, and it's only, I think, decades later that he realized that this was in, I think in the end of the 1910s or the early 1920s, and it's only in the 50s that he realized that people were still studying the model, and that it bore his name and everything. So. Okay, so now let's try to see. Okay, so the result in itself is not that interesting, or at least I've not solved it very well. Well, okay, there are a few interesting consequences. So, for instance, you can check that a few things occur. So this can be left as exercises. The limit when h goes to infinity of n beta h. So when you take the magnetic field the external magnetic field to infinity, basically all the spins tend to point up. So the magnetization tends to 1. So this is kind of natural, but you can check it from this formula. Well, so all of these are exercises, and beta h is equal to -1. And the other thing, which is maybe less intuitive, is that when if you take the limit when beta goes to infinity of m beta h, then this is equal to 1 if h is positive, 0 if h is positive, if h is equal to 0, and minus 1 if h is negative. So what this says is that basically when beta goes to infinity, all the spins want to be aligned with their neighbors. I mean, eventually, they want to be aligned, but they have to choose a direction. The direction they have to choose is given by the magnetic field. Okay, so if h is positive, even tiny, all the spins will want to align with h simply because it's better for all the spins to be in the same direction. And the most favorable of the two directions is the one with the h positive. Okay, and this is kind of m beta 0 equal to 0. This is just by symmetry. So, and this is just also by symmetry. Okay, so any questions about the result? Okay, so what is this expression here? It's just the largest eigenvalue of some 2x2 matrix. So, okay, let's try to see how this matrix appears into the game and how we get this value out of it. Okay, so maybe let me first say what we are going to prove. So, okay, we have to select. I mean, in order to get the free energy, basically, we have to take a sequence of boxes that extend to ZD in the Van Hoff, that exhaust ZD in the Van Hoff sense. Okay, what we are going to take here is simply lambda n is equal to this. Okay, so it doesn't exhaust ZD in the Van Hoff sense, but as I told you, it's only the third point which is important, and I mean, the size of the boundary of this is 2, the size of this is n, so I mean, if you prefer, you can take minus n, but it just makes the notation worse. So okay, so we'll take this box. I will write Zn for Z lambda n, because this would be just better. And what I will show is that the limit when n goes to infinity of 1 over n log okay, the fact that we will use is this. This okay, so where here, I mean, plus is just the whole okay, I mean, this sits at the place where the boundary condition is. So by plus, I just mean the configuration on Z where all spins are plus 1. Okay, and by minus, I just mean the configuration on Z where all spins are -1. So instead of considering just one partition function, I'm just going to sum the partition function with plus boundary condition and the partition function with minus boundary condition. Okay, this will become obvious why I do this in the computation, but what I'm telling you is that taking the sum of the two doesn't change anything. Well, okay, you can just check that if individually the two converges to this, and taking the sum, it converges to the same thing. Okay, so just check that this holds if you know. Okay. So now let us look at Z and beta H. Eta. And let's try to write an expression for this. Okay, yeah, maybe we'll just take a 5-minute break before I start the computation. And, because we are starting something different, so it's good to have a small breathing. I'm starting to be less sharp, so I think it's better. So let us resume and now compute the partition function of this system with an arbitrary boundary condition. Okay, so this is just, I'm just going to write it. This is just the sum over all spin configuration of exponential h and lambda beta h eta. Okay, so this sum, I can write it as n sums. Okay, I just sum over the value of sigma 1, sum over the value of sigma 2. So this is the sum over sigma 1 in minus 1, 1 times the sum over sigma n in minus n, n. And then I have an exponential. And then here I have two terms. So I have beta. Okay, and I have a sum from, so now I have, write this. We have a segment with n vertices and two boundary vertices. So we have n plus 1 edges. Okay, so this is the sum from, so here I have sigma x, x plus 1. And I have to sum over x from 0 to n. Okay, then here I have taken by convention that sigma 0 is equal to eta 0 and sigma n plus 1 is equal to eta n plus 1. Okay, this is just a definition. Okay, you see that sigma 1 to sigma n, they are the variables of the sum, but sigma n plus 1 and sigma 0, I have to give them a meaning. Okay, and then I have a second sum, which is the sum over x equal 0, 1 to n of sigma x times h. Okay, so maybe, okay, I don't know, maybe it would be nice to have the same sums here and there. Same set of indices. So maybe I should put a 0 here. But in that case, I have to put here some exponential minus sigma 0 h, which is not a problem because this is not something you're going to see in the limit. Okay, so now I'm going to define a xi prime. Okay, A is going to be a 2x2 matrix, and my coordinates, instead of being 1, 2, 1, 2, they are just plus 1, minus 1, plus 1, minus 1. Okay? So, I have two coordinates, which are spins. Okay? And I want A to be exactly equal to exponential beta xi prime plus h xi. Okay, and now if I have this, if you write A as a matrix, and here if it's plus, minus, what you get here is exponential beta plus plus h, exponential beta minus beta plus h, exponential beta minus h, exponential minus beta minus h. Okay, plus means plus 1 and minus means minus 1. Okay, so why am I introducing this matrix? It's just that this is just A sigma x1. So what we have is that A and beta h eta, it's equal to exponential minus eta 0 h, okay, times the sum over sigma 0 in minus 1, 1, sigma 1, the sum over sigma n in minus 1, 1. And then I have the product from x equal 0 to n of A sigma x plus 1. Okay, so this definition does not come out of nowhere. It's just the expression that I have here. I've just taken the sum out to make it a product. Okay, so you know that okay, you know how to make a matrix product. Okay, so in generally, when you have if you want to compute AB of ij, what you do is you take the sum over k of aik bkj. Okay, this is how matrix product works. And I mean, this also works for product of 3 matrices. So if you look at this, well, this is just the sum over KL of aij, bj, aik, bkl, cl, k. I mean, you can just, I mean, if you've never seen that, well, it's something you can do by induction, okay, on the number of factors you have in your product. Okay, because this sum over L here gives you BC of, sorry, it's a J, of KJ, and then you have a product of 2 matrices. Okay, so, and here, I mean, okay, I have arbitrary I mean, here I have product between arbitrary rectangle matrices, and I mean, the dimension has to fit so that the product makes sense, and I'm summing k over the right range, okay? So now I have exactly this, okay? I have a big product where I'm summing over all possible intermediate coordinates. So this whole thing here, this is just equal to a to the power n plus 1 evaluated at sigma 0, sigma n plus 1. Okay, so in particular, and what I have is that Z and beta H plus, okay. I'm not going to use this. In fact, I'm going to use the fact that, well, exponential minus H, exponential. Okay, this is also true. Okay, and no. Okay, this is true, but this is what I'm going to use. Okay, so I'm just taking this guy over there for personal convenience. So what I have is that exponential h times this plus exponential minus h times this, it's equal to a n plus 1 plus a n plus 1 minus minus. So it's just a trace of a to the n plus 1. Okay, so now the trace of a to the n plus 1, it's equal to lambda 1 to the n plus 1 plus lambda 2 to the n plus 1, where lambda 1 and lambda 2 are the two eigenvalues of A. Okay, so we'll see in a moment that these two eigenvalues are positive. So what I have is that the limit when n goes to infinity of the log of the trace of a n plus 1, this is simply the log of the largest value, eigenvalue of the matrix. Okay, so basically we just have to show that this thing here is the largest eigenvalue of A. And we will have done our job. Okay, and you see that you don't need you don't need the expression in order to compute it. This comes naturally. You just have to make a computation about A. So is everything clear about this matrix computation? Okay, so this thing about the trace, it's not completely necessary, but basically I want to make sure that, because if I'm not in a degenerate case, basically all the coefficients of my matrix, they will grow like the largest eigenvalue. Okay, so a priori one of them would be sufficient. But if I have the trace, I don't have to worry about that because I know by the trace formula, I know that the trace grows at least like exponentially like the first eigenvalue. Okay. So what we are going to do is to compute the trace and the determinant of A in order to diagonalize it, basically. So here was a minus. the trace of A is equal to 2 exponential beta times hyperbolic cosine of H. Guess. The determinant of A, it's equal to exponential 2 beta minus exponential minus 2 beta. So it's 2 times hyperbolic sine of beta. Yes? Okay, so now I'm trying to resolve the okay, so this is the sums of the eigenvalues. This is the product of the eigenvalues. So if I want to have the eigenvalues, I just have to solve this polynomial. So if I take the reduced determinant of this, which is b squared over 4 minus ac, I get that this is equal to, okay, so b is just exponential 2 beta cos h square minus 2 sinus h beta. And now I get that my two eigenvalues are lambda equal, well, square root of delta prime plus b over 2. Okay, so this is just the right thing. So square root of, no, sorry. It's b over 2 plus or minus square root of delta prime. Okay, this is always positive, right? Because this exponential 2 beta.
I think it's hyperbolic sine of 2.
Yes, it's hyperbolic sine of 2 beta. So this thing is always positive, well, simply because this thing is larger than 1. Okay, and when this thing is 1, this thing is simply exponential 2 beta is larger than 2 hyperbolic sine of 2 beta. Okay, just because the difference is equal to exponential minus 2 beta. Okay, so I guess we're done. So my eigenvalues are equal to this one, to this. So b over 2 is just exponential beta cos hyperbolic cos of h plus square root of, well, exponential 2 beta cos h square plus 2 sine 2 beta. Okay, and of course the largest eigenvalue is the one with the plus, and this is it. Okay, so this is the conclusion of the computation, okay, so I'm not so familiar with it, but this idea of using matrices to make explicit computation about partition functions is something which had other application in statistical mechanics. And the idea is that, I mean, this is a very simple case to apply it, but a priori you could apply it into higher dimensions. So the thing is that in higher dimensions, if you want to write things as a product, well, okay, let's say you are in 2 dimensions. What are the entries in your matrix? They will not be just +1, -1. There will be lines of spins, okay? Because basically, if you're in a square, okay, what you will be able to say is that, yes, this line interacts with this line in a certain manner, and this line, okay? And what you get overall is a product of all these interactions. And therefore, yes, you can write this thing as the trace of a matrix, but the matrix depends on n, and the dimension of the matrix is 2 to the n. So that starts to be nasty. But I think this is basically the starting point of the resolution of the Ising model in dimension 2. So basically, when you have a problem like this, then you have to try to find simplification in your computations. And yeah, I should, at some point in my life, I should just look at these old papers and to see how things were done at the time. But okay, let me basically tell you what the result is. So what is the best you can do in dimension 2 and more? Okay, so it's the best in terms of exact computations, okay? So in dimension 3 and more, you can't do anything, so that's quick. In dimension 2, so it's not possible to compute the free energy in general, but it's possible, okay, to compute the free energy at 0 magnetic field. So this was done by Lars and Zeiger in 1944. And here is the formula you obtained. So log 2 plus 1/8 pi square integral over 0 to pi, integral over 0 to pi, log cos hyperbolic of 2 beta minus sine hyperbolic of 2 beta times cos theta 1 plus cos theta 2 d theta 1 d theta 2. And I guess I have to end this thing here. Okay, so the thing about this function is that it's not analytic, or it's analytic everywhere except at one point. And this point is beta equal to 1/2 over log 1 plus square root of 2. And okay, maybe it doesn't look like this tells you a lot about the system, but a few years later, the same person claimed to have a formula for the spontaneous magnetization. Okay, and here you will see very well that it's not analytic. The formula he has is 1 minus 1 over sine hyperbolic square of 2 beta square. You take the positive part of this, and you take this to the power 1/8. Okay, so in particular, you get that m star beta is equal to 0 if beta is smaller than beta c, and that m star beta is positive if beta is larger than beta c. Okay, so the system has a phase transition at beta c from a system where you have no spontaneous magnetization to a system where you have spontaneous magnetization. Okay, and in fact, this was a claim. He never gave the proof, but somebody gave the proof 3 years later. Okay, and so all of this is really beautiful mathematical work, kind of old school with lots of computations. And what's kind of remarkable is that Onsager is not a mathematician, he's a chemist, or maybe also a bit of kind of a theoretical chemist. And well, he's not only a chemist, he won the Nobel Prize in chemistry. And okay, maybe to give you some kind of link with what we have done so far. So I mean, even though this result is really old, there is no super easy proof of the computation of beta c in dimension 2. Okay, and I'm not going to do that in this class. But what we are going to do now is move forward and basically prove the existence of BC without trying to compute its value. Okay, which is already something interesting, and it shows that we have a phase transition in dimension 2 and also 3, and like in every dimension larger than 1. But there is a proof for the value of beta c that doesn't use transfer matrices. And which is, I think, something like a bit more than 10 years old. And maybe in order to understand it, to see how, well, to have an idea of where what's the relation with what we have seen, you can just check that exponential beta c, and really exponential beta c is kind of what matters in the formula. This is equal to square root of 1 plus square root of 2. So just the kind of thing that we have seen before with the self-avoiding walk on the honeycomb lattice. And it turned out that there is a proof of beta c equal 1/2 of log plus square root of 2 using parafermionic observables. Okay, so what do I mean by parafermionic observables? Basically, you cook up a quantity that is defined on the lattice that is discrete analytic. You integrate it on a contour, and you try to get something out of it. And This is by Duminil-Copin, by Beffara and Duminil-Copin. And I've not checked my references before coming, but I think it's around 2012. Okay, so this is all for today. Starting on Friday, we will try to look for a proof of phase transition dimension 2 and more, and look at this thing of limiting measures. And for this, a really necessary ingredient will be the proof of correlation inequalities. So what we are going to do is basically prove the true FKG inequality, which states that, well, okay, spin configuration is a bunch of +1 and -1, so you can put order on that. Okay, just saying a spin is larger than a spin configuration is larger than another one if I have more pluses. Okay, I mean if coordinate-wise I'm larger. Using this, you can define a notion of increasing events. And the idea is that for under the Ising measure, increasing events are positively correlated. Okay, so it's a bit more subtle than for percolation, but the idea is that if you already have more pluses, basically not only you will be able to use these pluses to satisfy the other event, but also these pluses, I mean, they will help other pluses to appear because they will, I mean, because of this nearest neighbor interaction term, okay, this beta sigma x sigma y, they will kind of help their neighbors to become plus. Okay, so this is one of the correlation inequality. There is another correlation inequality which is easier to prove, but for which I have, well, I think for which the intuition is less obvious, which is called the GKS inequality. And using these two things, okay, we are going to start our quest towards existence of phase transition. Questions? Okay, so see you on Friday.